Good evening, everyone. My name is Derrick Tang, and as my senior thesis for the Science and Technology Department, I built a 3D printed robot hand. If we were to describe my experience at Nichols, it would definitely be, in the direction of science and technology. I was one of the founding members of the robotics team. I was in the engineering class. I was also a member of Science Olympiad, and I just have a profound respect for science and technology. I found an opportunity to sort of demonstrate and capture everything I've learned about science and technology over the years. This year marks the first year of our 3D printing program, which is led by Mr. Conrad from the IT office. I've heard of the vast potential of 3D printing. It can print anything your heart desires. So I asked Mr. Conrad to be my senior thesis advisor. And I decided to make a hand after I was browsing through a magazine. Pardon me. This very magazine. It's called Make Magazine. This guy on the front cover, his name is Nicholas Hutchett. He is an amputee who built his own prosthetic hand using 3D printing. He accomplished this by using open source files of an actual fully built robot called InMove. He basically printed out these files and built himself a hand using nerve sensors. The title of the article that he's in is How I Made My $250 Robotic Arm. $250. That's huge considering that most professional prostheses go anywhere from $8,000 to $80,000. This means that anybody with internet access, a mailing address, a 3D printer, and the ability to download these files can create their own 3D printed robotic hand. So, how do you 3D print? Well, anything you put in a printer has to start out in a type of CAD software. CAD stands for Computer Automated Design. The CAD software I use is called SolidWorks. SolidWorks has been around since its first release was in 1999. Every year since then, it's had at least one new release per year. It's constantly updated on. It's one of the most popular academic and industrial types of CAD softwares. My personal experience with it, I love SolidWorks. It's a very flexible, very intuitive type of software. It's a joy to learn, and it has the best editing power of any type of software I've ever seen. So, using SolidWorks, I designed a total of 19 parts in this hand in about 40 hours of designing in front of my laptop. And I put all these parts into a type of file called an assembly in SolidWorks. You make parts, and you can make assemblies of parts. I put all 19 parts into this one assembly, and by using a mate tool, I can actually constrain all the different parts that I made to act exactly how I want them to. Meaning, I can actually have a hand in the software and pose it however I want, and check to make sure, are any of the parts clipping? Is there too much friction here? Can I, get the desired range of motion that I wanted? And sure enough, when I did print it out, I made no design errors at all. Everything came out perfectly the first time, and I was able to build my hand straight from that. To get from the SolidWorks program and all the different 19 parts into the 3D printer, you have to convert the SolidWorks files into what's called an STL file. STL stands for stereolithography. It basically converts the ideal geometric model inside the software into polygons that the cube can recognize. It took a total of 15 hours to print all 19 parts, and about 1 hour just to build all the parts because everything fit perfectly using that assembly feature to make sure everything's okay. So, once I have this hand, how do I bring it to life? Well, let me show you. It might be a little hard to see. I'll try to speak loudly so you can all hear me. I'll tip this forward. This is the prototype one I made of all the different parts on it. We have, here's the glove, I'll get to that, the glove, but here's the 3D printed hand itself, the last piece back. All parts of the hand besides the bolts were 3D printed, and I could actually, with the power of SolidWorks, I can actually print out each of the bolts the exact size we need and put it all together like that. But to save time, I use to the bolt. We'll see if we find that hardware. I designed my hand to mimic the gestures of a real hand, but that's what the glove is for. And I accomplished that using flex sensors. All the flex sensors right here are taped down, but this is a flex sensor. This is a type of variable resistor, and in a circuit, the Arduino brains are using. Arduino is a type of cheap brain from Italy. It runs for about $20. Super cheap, super versatile. And for this project, I used 5 Arduinos and 3 breadboards for all the circuitry. As I was saying, these are flex sensors. I have 5 of them on here, 1 for each finger. And flex sensors are variable resistors, meaning in a circuit, depending on which position the flex sensor actually is in, you can adjust the voltage drop across the position. Using that, the brain can actually measure what position it's in. That's how I measure standard set of information. And using that, I can tell each of the Arduinos to put a servo in this exact position using C++ code. So I used a bit of coding in this project. Again, I have 5 Arduinos, 1 for each of these 5 servos. And each of these 5 servos runs a 65-pound braided fishing line that extends to the end of each one of these fingers. And I think that's it. Again, this is just a prototype board. We just threw this together last minute. And we use breadboards, we use pins for this. So, if I put on this glove, this has been on for a while, so I'm not sure if it will work exactly as it was before. We can bring this somewhat. Of course, not all projects are perfect, and one design feature, I guess I sort of overlooked. The design problem I was having is there are 2 types of motions for hands: flexion and extension. Flexion is bringing your hands in, and extension is bringing your hands out. And these are accomplished by string-like tendons with muscles originating from the forearm. The only thing muscles do are pull. The reason why you pull it out is because you have tendons along the back of your hand. They run through the carpal tunnel all the way up here and attach to the bone. And that's how you produce both a flexion and an extension. I thought I could replicate that. I thought I could replicate nature using 2 strings in each of these fingers. But I tried that, and I was only able to produce a flexion. So I guess, so for an extension as like a quick fix for the presentation today, I put some elastic on the back of each of the fingers to try to have an elastic restoring mechanism. But it doesn't seem to work too well. Again, this is just a prototype. So, and I'll show you the circuitry is buggy, but I do get something to I take these flex sensors to the back of each of these things and wire that straight to each of the other areas. So, same thing there. I just use my own hand to sort through this one. Some hands move. Earlier today, I got all 5 servos working, and all 5 Arduinos working. Apparently, 1 of the 10 doesn't want to work right now. Several of the 10 work. But I can get something. When it did work, it was quite impressed. I could make a fist and I could make a peace sign, give a thumbs up, and I could give a bird. I mentioned this like 3 times already. I said it 4 times. It's just a prototype. To this project, we could trade this breadboard in for something that more substantial. We could solder each of the pins into a different type of circuitry board and have a permanent connection, so you don't just unplug something like that works and something like that works. Also, concerning the flex sensors, these flex sensors are pretty bluish. There's a bunch of other ways you can hook up sensors to tell you what to feel. You can use, for example, on Xbox Connect to track the motions of your fingers to imitate it that way, drive the servos a similar way. Although I'm graduating this year, I hope more underclassmen recognize the vast potential of 3D printing in robotics and product aesthetics. There are many adults and students at this school really excited about the growth of our technology program. This passion never fails to us. We're on the threshold of many great things and much learning, much mutual learning. I'd like to thank Mr. Coburn, Mr. Hiller, and Mr. Conrad for teaching me the skills to do a project like this. With that, thank you.